Good evening, all of you. Is the video and audio clear to everyone? Any questions, any doubts for anybody? So please ask if you have any other queries. All right, then let us start our session. So we discussed about the polynomial rings. So I just want to mention one result that so you consider the polynomial ring f of x where f is a field, and what could be the ideal structure here? In other words, if you consider the polynomials of the form, then what type of form determines the ideals in the polynomial ring? So the answer for this is, if you consider the polynomials where constant term is absent, so if you consider the set of polynomials where constant term is not there, such type of polynomials will become an ideal in f of x. Is it audible to all now? Say. Right. So please take a note of that point. Another important one is so what I am saying, if you want to consider the ideal structure in f of x, in other words, if you consider the polynomials with certain kind of property, they will become an ideal. So what type of polynomials we need to choose so that it will become an ideal? So the question here is the solution. So you consider the polynomial where constant term is not present. So generally we write the polynomial like this. Accepted? This is the general notation of the polynomial we write. A naught plus a1x plus so on plus an x power n. Accepted? Yes or no? So in this you remove the constant term. So this type of polynomial, if you write them as a set, they will become the ideal in f of x. Clear? So for example, you consider the set of polynomials of this form. So this is u of x. Now I am going to prove this. This will become an ideal in f of x. So it must satisfy the two conditions of the ideal in U. So if you take two polynomials, say the first polynomial is b1x plus b2x square plus so on plus bnx power n. Another polynomial is you have taken c1x plus c2x square plus so on plus cmx power m. This is a polynomial f, this is a polynomial z. Now let us consider the difference for them. So if you consider f minus g, this is equal to b1 minus c1 into x plus so on plus the terms will come. So the final coefficient will be CR x power R, where R indicates the maximum of the 2 degrees. Because whenever you perform addition and subtraction for the polynomials, we don't know the degree between these two, among the two numbers n and m. Which polynomial is having higher degree, we don't know. So if you consider addition or subtraction, the resultant polynomial will have the degree which is maximum among these two numbers. So while considering, as simply we are performing the difference between the coefficients of like powers. So b1 minus c1, b2 minus c2, and so on, it will continue. So the end coefficient will be CR XR, where R indicates the maximum among m and n. Okay? Are you clear with this? And if you observe that this is a polynomial where constant term is absent. Therefore, obviously, f minus g will belong to the set u of x. Therefore, u of x satisfies the first condition of the ideal. You please take a note of this. Are you clear? Or any questions for you? Yes or no? Are you getting the idea on what I am saying? Right? Please understand, I am taking the polynomials where constant term is not there. Please understand. Constant term is not there. Such type of polynomials I am considering in u of x. Okay now? Right. So if you want to consider the second condition, so you take a polynomial f belong to u of x, and you take any polynomial in f of x. Say I have taken that h of x is equal to a naught plus a1x plus so on plus am x power m. This polynomial I have chosen here in f of x. So if you consider the product, so f of x into h of x, we know how to define the product of polynomials. So in the first step, we multiply constant term with constant term. Here the constant term is a naught, here the constant term is 0. So this is a naught dot 0. Then we consider the x coefficient. It will come as a naught b1 plus b1 a naught, b1 into a naught plus a1 into b naught. This is the coefficient of x, and you will get the remaining terms. Now the important thing is, whatever the degree of the polynomial, that doesn't matter. The fundamental thing is, if you want to say that the product is belonging to the set u of x, constant term should not be there. It must be a polynomial where the powers are having from x power 1 to x power something. Since here the constant term is not present, it has become 0. So this is a polynomial which contains the indeterminate x having powers from 1 to higher degree. Right. Therefore, this polynomial by default belongs to u of x, hence it becomes the ideal. Right. So, in general, while writing the ideal structure, we write that the multiples of x, that we call it as the ideal in the polynomial ring. You please take a note of that. Right. I already mentioned that division algorithm holds So what is meant by division algorithm? Whenever you consider the polynomial ring f of x, you take any two polynomials here, f of x and g of x in the polynomial ring, where g of x is a non-zero polynomial. Now, immediately you can find two more polynomials, q of x and r of x, such that we can write f of x is equal to g of x into q of x plus r of x. The division algorithm property. So, dividend is equal to divisor into quotient plus remainder. Now, what happens? The remainder will be zero polynomial, or degree of r of x must be less than degree of the divisor, that is g of x. So, either the remainder will be zero, or degree of the remainder must be less than degree of the divisor. This property will hold always in the polynomial ring. Okay? So especially we consider as and when you take a polynomial ring over the field f of x. So division algorithm always holds in f of x. So proof of this result is not required. We will go for the other result that we discuss. So please take a note of this, then mention after noting. So one more result is, you consider f of x belongs to f of x, and you take that degree of this polynomial is either 2 or 3. Then what happens? The polynomial what you have taken is a reducible polynomial if and only if it has a root in the field. You take a note of this result. So we have taken a polynomial f of x belongs to f of x, and the polynomial degree is either 2 or 3 that I am taking as a constraint. Now the condition is that if the polynomial is reducible, then it always contains a root in the field f. Okay? If you have noted, I will go with the solution. Shall I continue? So it is an if and only if condition. So let us start with the main part. So let us assume that f of x is reducible over f. Then from the very definition of f, we can write f of x is equal to product of two values where g of x and h of x are non-constant polynomials. Where g of x and h of x are non-constant polynomials. Now what happens? As per the choice of f, degree of f is either 2 or 3. So if you take that, the degree of f of x, so from its value, it is nothing but degree of g plus degree of h. In the given data, degree has only two possibilities for f. So if degree of f is 2, since the polynomials here are not constant polynomials, so the only possibility is 1 and 1. Because the sum is giving 2. If degree of f is 3, then the respective polynomials degree will be, for the first one it is 1, for the second one it is 2, or 2 plus 1. This is the possibility. So whatever the situation you consider, among the two polynomials g and h, one polynomial always has degree 1. It is nothing but it is a linear polynomial. So as and when you mention it is a linear polynomial, it will possess the root. Because if you say that degree of g of x is 1, then it will be of the form x minus alpha, where x has power 1 is a linear polynomial. Hence we have written that f of x is equal to x minus alpha into h of x. Therefore, it is written as product of two values, and if you substitute alpha here, f of alpha is nothing but 0. Therefore, alpha is the root of the function. Okay? That is the solution of the main part. Please check. Are you clear? Yeah. Here, degree of g of x is equal to 1. Accepted? So, g of x is a linear polynomial, a first degree polynomial. So what could be the pattern of a first degree polynomial? G of x will be of the form ax plus b. Accepted? Yes or no? So this can be modified as x plus b by a. Also you can write it as x minus of minus b by a. Agree? So is it in the form of x minus alpha or not? So that is what I am saying actually. Since degree of g of x is 1, it can be represented as a linear polynomial like that, x minus alpha. So f is equal to g into h. From that, g is nothing but x minus alpha. So f is equal to x minus alpha into h. Therefore, this alpha will become root of this equation. Agree? So now we start with the converse part. So conversely, let us assume that f of x has a root in f. And let us take that, say, alpha is the root. So if alpha is the root, then by default, x minus alpha is the factor. Therefore, you can write f of x is equal to x minus alpha into something. For that thing, I can take any value. Let us say this is p of x. Now what happens? As per the problem considered, degree of f is either 2 or 3. So, in this you can say that if degree is 2 here, then obviously since it has degree 1, it must possess degree 1. It has no other alternative. If degree of f is 3, it has degree 1, it must have degree 2. It has no other alternative as per the given data is considered. So whatever the situation may be, f is written as product of two polynomials where both the polynomials are not constant polynomials. It has a standard degree, it has a standard degree. Therefore, this is the definition of reducible polynomial. What is meant by reducible polynomial? Whenever we take a polynomial, it is possible for us to write it as product of two polynomials where both are non-constant polynomials. That means each one is having degree greater than or equal to 1. So here it has degree greater than or equal to 1, here it has degree greater than or equal to 1, hence f is a reducible polynomial. You take a note of that one. After noting, please inform. Any questions for anybody? Right? So let us take the next result. So if you consider the polynomial ring f of x, it is always a principal ideal ring. So whatever the ideal you consider, it is always a principal ideal. That we proved it now. So in the polynomial ring f of x, you take an ideal u of x. So it contains two possibilities. So the ideal what you have taken may be a zero ideal. That means it contains zero polynomial only. Secondly, it contains non-zero polynomial. It has two cases. So if you take the first case, this is a trivial case. If it is a singleton set having zero polynomial only, by default it is a principal ideal because it is generated by zero. So if you consider the second case, so u of x contains non-zero polynomials also. That we can consider. Right? So in this situation, we will get two things. Now you take a polynomial, g of x belongs to u of x. While selecting the polynomial, you have multiple choices. So if g of x is a polynomial, then obviously the possible choices of selecting g of x is it may be a constant polynomial or it may be non-constant polynomial. If it is a constant polynomial, then generated by g of x is equal to the whole ring f of x. Therefore, f is generated by this element, therefore it becomes the principal ideal. Please observe again. Our intention is, if you consider a polynomial ring f of x, then it is always a principal ideal ring. It means that whatever the ideal you choose, it is always generated by some element. So for this, I have taken that u of x is an ideal in f of x. So here you have two choices. The ideal what you have taken may be a zero ideal or non-zero ideal. If it is a zero ideal, it is a trivial case, trivial situation. By default, it is generated by zero. Hence, this is the principal ideal. If it is a non-zero ideal, means it contains non-zero polynomials also. Then you select a polynomial in u of x. So while selecting the polynomial, you have so many possibilities. So the fundamental possibilities are two. Either the polynomial may be a constant one or a non-constant polynomial. If it is a constant polynomial, then generated by g of x is equal to the whole ring f of x. That is what I am saying. Clear? Please ask any queries if you have. Yes or no? Right. Now, if it is a non-constant polynomial, that means it has degree either 1 or more than 1. That is the other case. So what happens? Let us take it contains a lot of polynomials u of x, in which you select a smallest degree polynomial, say h of x. So h of x be the smallest degree polynomial in u of x. As we know, division algorithm always holds in f of x. We can apply division algorithm. So what is our intention? We have to show that u of x is generated by some value. That is our actual intention. As you have chosen a smallest degree polynomial in u of x, so I am giving the name as h of x for it. My intention is this h of x generates the whole set u. So what does it mean? Whatever the polynomial you choose in u of x, that can be written as a multiple of h of x. That is our intention. So for that, you take a polynomial in u. So you take that, say f of x belongs to u of x is any polynomial. Immediately, by applying the division algorithm, you can write f of x is equal to h of x into some polynomial, say q of x plus r of x, where q of x and r of x are polynomials in f of x. And what are the possibility of division algorithm? Either r of x will be a 0, 1, or degree of r of x is less than degree of h of x, because here you are dividing with h of x. H of x is the divisor, r of x is remainder, q of x is the quotient. So what I am saying, r of x is 0 is compulsory. So this situation will not happen. This is the only situation. So if r of x becomes 0, so you have written that f of x is equal to h of x into q of x. It means that every polynomial f taken in u is a multiple of h. Therefore, h of x is generating the whole set u. Therefore, it is a principal ideal. Now the question is, why it is 0? Why the remainder is 0? If remainder is 0, if remainder is not equal to 0, then what happens? Let us check. Suppose r of x is not equal to 0 polynomial. So this is the pattern for us. We have taken u and you have taken f. So in u, one polynomial what I have taken is f. And I know that h is the smallest degree polynomial in u. And while writing division algorithm, q and r basically belong to f. So since u is an ideal, applying the ideal condition, hq belongs to u. Since f belongs to u, hq belongs to u, u is an ideal, applying the ideal condition again, f minus hq belongs to u. So from this very equation, f minus hq is nothing but r. Therefore, r of x belongs to u. And one more property is, if r of x is not equal to 0, then obviously degree of r must be less than degree of h. So degree of r of x is less than degree of h of x. This is a contradiction. Contradiction to what statement? I have initially taken that h of x is the smallest degree polynomial in u. H of x is the smallest degree polynomial in u. So here what occurred? R of x is a polynomial which is belonging to u, and R of x has degree less than h. This is a contradiction to the small nature of h. Therefore, this situation should not happen. Hence, the only possibility is R of x equal to 0. Hence, f is a multiple of h. Therefore, u becomes principal. So please take a note of that. After noting, please inform. Is it noted? Say. Fine. Any more queries for anybody? So another interesting result is, in the previous class, one question arisen that if you take an irreducible polynomial and if you consider the ideal generated by an irreducible polynomial, then is it maximal ideal or not? That we discuss now, right? So the statement is, an ideal generated by P of X in F of X is maximal if and only if P of X is irreducible polynomial. If and only if P of X is irreducible polynomial. You please take a note of that. So ideal generated by P of X is maximal if and only if P of X is irreducible polynomial. Take a note of that. Is it noted? Now, it contains main part as well as converse part. So let us go with the main part. So main part is, we are supposing that P of X is maximal ideal. So we know that every maximal ideal is prime ideal, so it will become a prime ideal. Now the interesting thing is, we have to show that it is irreducible. Since we don't know with what polynomial we are dealing, we don't know what is the exact value of P of X. So in the negative way, we prove the result. So let us assume that P of X is a reducible polynomial. Then we start the procedure. We will get a contradiction. Hence, our supposition must be wrong. It should be an irreducible polynomial. That is the pattern we apply here. So if you say that P of X is a reducible polynomial, then from the definition of it, we are able to represent P of X as product of two polynomials. So you can write P of X as R of X into, say, S of X. product of two polynomials is possible, and hence if you consider their degree, so 1 less than or equal to their degree is less than a degree of p of x. So you are writing them as proper factors. So you can write p of x is equal to r of x into s of x, where the degrees of them 1 less than or equal to the degree which is less than p of x. Because if among these two, one degree is equal to degree of p of x, then one polynomial is nothing but the constant polynomial, therefore it becomes irreducible. But we have started that it is an reducible polynomial. So as we know that x divides x like a divides a, so p of x divides p of x. Since p of x has value this, so we can say that p of x divides r of x into s of x. So since it is prime ideal, from the definition of prime ideal, we can say that clear? So if you have a small doubt how this situation has happened, actually we know that the polynomial p of x belong to the ideal generated by p of x. So p of x is equal to this. Therefore we can say that r of x into s of x belong to this ideal. Since this is a prime ideal, whenever the product belongs to the ideal, one of the element must belong to this. So we can say that r of x must belong to generated by p, or s of x must belong to generated by p. So whatever the case you consider, always either p of x divides r of x or p of x divides s of x. And one more thing is, the degree is less than degree of p as per this supposition. Now the question comes, you are saying that degree of p is greater than degree of r as well as degree of s, and you are saying that the larger degree polynomial is a divisor of the smaller degree polynomial here. This is basically a contradiction. How can a third degree polynomial will divide the second degree polynomial? It is basically wrong. So why you get a contradiction here? Because we have taken that it is a reducible polynomial. Hence it must be reducible. That was the conclusion. Please observe and tell. So if you get confusion over the board representation, I will simply give a small diagram for it. What is the logic behind it? Can I? Is it required or not required? Okay. So if we have noted the main part, I will start with the converse part. Okay. You mean that just draw a small picture, what is the strategy in doing this? Am I correct? Yeah. So this is the thing. So our assumption is this is maximal ideal. So implies it becomes prime ideal. So in the opposite way, take that P of x is reducible. Then what happens? We write the reducible definition. So P of x is equal to product of two values. Each has degree less than p, less than p degree. Now, using prime ideal condition, either R of x belongs to generated by p or S of x belongs to generated by p. So that is either P of x divides R of x or P of x divides S of x. This is a contradiction. Why? Because P of x has degree greater than R and also greater than S. How a higher degree polynomial divides the smaller degree polynomial? Therefore, our assumption must be wrong, hence it must be irreducible. That was the logic. Please observe that. Is that okay now? Any more queries for anybody? Then I go with the converse part. So, in the converse part, assume that P of x is irreducible. So, we have to show that it is a maximal ideal. So, let us go with the definition of maximality. So, you take that generated by P of x is a subset of some ideal. This is subset of f of x. So, earlier to this result, we have proved that whatever the ideal you consider, it is always a principal ideal because f of x is a principal ideal ring. So, whatever the ideal you write, it is a principal ideal. So, in order to prove maximality, if you consider the hierarchy like this, generated by P is subset of something, it also must be a principal ideal. So, here you take that this is the ideal generated by G of x. So, this is the hierarchy for us. Now, this thing will belong here. Therefore, P of x belongs to generated by G. It means that you can write P of x is equal to G of x into something. Please observe. Any questions up to this step? Yes or no? Any questions up to this step? Are you clear? Now what happens, as we have taken that it is irreducible, then by default from the definition of irreducibility, among these two polynomials, one polynomial must be a constant, because irreducible means you cannot write it as proper factors. So one factor must be an improper one. So either G or H must become a number. So in other words, either G or H a constant polynomial. If you take that G is a constant, so it is a number. So then generated by G is equal to generated by F. I mean the whole ring F of X. Because the polynomial ring is generated by the constant polynomials. Therefore, we have proved that these two are equal. Hence, P becomes maximal. If H is constant, it means that H has become a number, say K. So you have taken that P of X is equal to G of X into the number K. Basically, if you write the polynomial, all the coefficients of the polynomial belong to the ring. Here the ring is F. So K belongs to F. Since it is a field, it has the inverse. So you can write G of X is equal to K inverse into P of X. Therefore, G of X is a multiple of P. Therefore, G of X belongs to generated by P of X. Therefore, P of X and G of X both are equal. We have proved that these two are equal. So whenever you consider the hierarchy, either these two are becoming equal or these two are becoming equal, hence it is the maximal ideal. Please check on that. If you have any other queries, you can ask. So are you feeling something difficult in understanding the concept of these polynomial rings? Let me know. Say. Are you comfortable or not comfortable? Any questions for this approach? Please tell. Or if I am going fast, please let me know. So shall I continue further? Right. So there is one more interesting result which is also based on the previous year question papers. Let me write it. Show that x square plus x plus 2 is irreducible over f, where f is equal to 0, 1, 2. modulo 3. And use it to construct a field of 9 elements. Use it to construct a field of 9 elements. So please take a note of the question, then we discuss with the approach. Shall I proceed? So here we have to show that this is an irreducible polynomial in the first case. So we know that reducible means it has a root. Irreducible means it has no root. So what is the field here? I have taken the set having 3 elements 0, 1, 2. If I have proved that these 3 elements are not at all roots for the polynomial, it means that it will become the irreducible polynomial. Accepted? Now you consider the respective values. Say if this is the polynomial f, you take f of 0, f of 1 and f of 2. You substitute and tell me you are getting 0 or not as an output. You are not at all getting 0. Therefore, it is an irreducible polynomial. Accepted? If you have a doubt, suppose I have substituted 2 here. It is nothing but 2 square plus 2 plus 2. So nothing but 4 plus 4, 8. Here the operation is modulo 3. 8 modulo 3 is nothing but 2. So you should not get 0 here. Similarly for 1, similarly for 0. Now, just now we have proved that whenever you have an irreducible polynomial, if you consider the ideal generated by it, it is always a maximal ideal. So, the ideal generated by this polynomial is maximal. So, generated by f of x is maximal. In the question, it is given that we have to construct a field of 9 elements. So first of all, let me say, I just want to construct a field, then I will tell that it will contain exactly 9 elements. Fine? Are you getting the overall idea? Yes or no? Right. So here what happens? We can consider the quotient ring. So the given ring is f of x. By f of x you consider. So this is the quotient ring. We know that this is maximal ideal, hence by the known result, this is the field. Quotient ring will become the field. You accepted? Any doubts? Because we have the result that R by I is field if and only if I is maximal. Have you solved this result or not earlier? Yes or no? So since this is the maximal ideal, quotient ring is nothing but the field. So this is our required field. So if you think about what will be the pattern of the elements in this field, let me say if you have written r by I, how do you write? Here we consider all cosets. If you take x here, x plus I will be a part in r by I, the respective coset. Here also, for our computational convenience, let us give a name here. So let us take this is equal to I. So f of x by I is the field. And what will be the pattern here? If you take any polynomial here, this plus I is the respective coset. So if you take, say, any polynomial p of x plus I is the value in the quotient ring. Clear? Yes or no? Right. Now, what happens? We know that division algorithm always holds in these rings. So, if you take any polynomial p of x in f of x, then by division algorithm, you can write p of x is equal to f of x into q of x plus r of x. So, where r of x is equal to 0 or r, degree of r is less than degree of f. Accepted? From the property of division algorithm. So from this very definition, you can say that p of x minus r of x is equal to f of x into q of x. Now what happened? The difference of these two polynomials is a multiple of f. So this is a polynomial, it is a multiple of f because f into something is giving this one. So therefore, we can say that p of x minus r of x belong to generated by f of x, that is I. Accepted? Please check the step. Any questions you can ask? Any questions you can ask? Right. Now see, here you got the result that p of x minus r of x belongs to I. So at this step, we can have a known result application that a minus b belongs to u if and only if a plus u is equal to b plus u. Can you recollect that result now? We did in the ideals and cosets. A minus b belongs to u if and only if a plus b, a plus u is equal to b plus u. It is also of the same form. So comparing these two, you have p of x plus I is equal to r of x plus I. Accepted? Now see, this is our field, the quotient ring, and we know that whatever the value in this field you have considered, it is of the form p of x plus I, where P of x is a polynomial in the numerator. I is the value in the denominator. So every polynomial, every coset in the field is of this form, P of x plus I. Just now we have proved that whatever the polynomial or the coset P of x plus I you consider, it is nothing but of the form R of x plus I. And what is the criteria of this R? This R is nothing but the remainder polynomial. So this may be either 0 or degree of R is less than degree of F. In the given data, F is nothing but the polynomial x square plus x plus 2. And what is the degree of this? It is 2. So from this, maybe you can take the 0 polynomial or the linear polynomial. So if you deal with the non-constant polynomials, degree of R is less than degree of F. So always R of x will be of the form ax plus b, the first degree polynomial, because degree of R is less than degree of F. So R of x plus I is nothing but ax plus b plus I. So every element in this field will be of the form ax plus b plus I. Is it clear now? Say. Yes or no? Fine. Now, as per the data, three things are asked in the question. First thing, the given polynomial must be irreducible. Second thing, we need to construct a field. Third thing, we have to show that the field contains exactly 9 elements. The first two are proved. Now we are going to prove that the field contains exactly 9 elements. From this very pattern, immediately we say that this field contains exactly 9 elements of this form. How can we decide that? It is very simple. Let me say, I have written a polynomial f of x belong to R of x. What does it mean? Whatever the degree of the polynomial, the coefficients are taken exactly in the ring R. So here, if I mentioned that f of x belongs to f of x, or here I am taking ax plus b belongs to f of x. So a and b are nothing but basically the values in the f. And in this problem, f is given as 0, 1, 2. So whatever the form of ax plus b you consider, a and b must be selected among the 3 values only. There is no other possibility. So you can select in different ways. You can take a and b as 0, a and b as 1, a and b as 2, etc. etc. You can take a is equal to 0, b is equal to 1, a is equal to 0, b is equal to 2. Like that, you can change the coefficients in ax plus b. So if you consider, the maximum possibility is nothing but 9. Please observe that. You take different values for a and b using the elements 0, 1, 2 only. The possible permutations 0, 1, 2. That's it. So the field is the quotient ring where every element is of the form R of x plus I. R of x is nothing but the remainder polynomial. Here remainder has the form ax plus b. So every polynomial ax plus b you are choosing in the field f of x. So the coefficients has only 3 choices to select from 0, 1, 2. So a, b should be either 0 or 1 or 2, the possible combinations. So you can observe that the possible combinations are nothing but total 9 combinations. If you have a doubt, let us write that. The small doubt if you have. So let us write the possible coefficients from that. So ax plus b, this is the polynomial you are going to write. You can take both a and b as 0, 0, 1, 1, 2, 2. This is the one possibility. You can take A as 0, B as 1, A as 0, B as 2. Now you fix A as 1, B as 2. Again, A as 1, B as 0. Another possibility, you take that A as 2, B as 1, and A again 2, B as 0. You can check that total 3 possibilities came. The total number of possibilities are nothing but 9 from the set what you considered. Okay? So if you have a doubt how to remember that, here the degree of the polynomial is 2. Here you have 3 elements, 3 square we can take into consideration. That is one observation. Okay? That is the solution of the problem. So this is the question asked in the previous year papers. There he asked to construct a field of 121 elements. There what happened? He has taken the values as 0, 1, 2, 3, and by calculating the remainder and writing the possibilities, you will get 121 elements there. The procedure is similar, the set is simply changed, that's all. Okay? Right? So, shall we continue or let us wind up the session now and we will meet tomorrow with new concepts? What do you say? Right? Then we will meet tomorrow with new concepts. So we are almost done with abstract algebra. The remaining parts to deal with abstract algebra is you have to take some problems based on Taylor theorem, that is one. You need to take the concept of unique factorization domain and some sample problems on it, UFD, unique factorization domain. And third, we need to deal with the field extensions. There you have some specific words like algebraic extension, normal extension, etc., splitting field. So covering these technical words, you have totally done with abstract algebra. Okay? These will be covered in the upcoming sessions. So we have covered 85% of this will be now. And I have taken mostly the possible questions from the previous year papers, the models as well as the similar questions. Okay? So you have different books. You can take one book that this is one book you take, Joseph A. Garian or V.K. Khanna, S.K. Bhamri. This is the other one. Or if you want to take something application oriented, you can take the book Dumit and Foote. This is you can take. So for the yes, finite fields is nothing but the field extensions, the upcoming topic. Right. Or you can purchase abstract algebra by either Sham series or S. Chand. So please understand one thing. While dealing with these textbooks, it will contain many questions, and majority of the questions with regard to UPSC point of view you can take, And the problem is it contains some unnecessary topics also. So by viewing the syllabi, you need to understand that. But syllabus description is not clear in this book. So if you start reading, it contains around 300 pages, the whole book. And where to start, where to go, you should have a clear idea for this. And for these books, either Sham series or S. Chand, generally they were given in 2 volumes, volume 1, volume 2. Sham series volume 1 covers group theory completely. Volume 2 covers rings and fields. S. Chand, it covers group theory as well as rings. For further extensions, you need to take advanced abstract algebra of S. Chand. That is the problem. So while dealing with abstract algebra, no author has written a single book to cover the entire syllabus of UPSC. That is the problem. However, you can refer Krishna series modern algebra. That will cover at the most 80 to 90% of the syllabus, covering the total one. Krishna series modern algebra that you can take. Okay. The fundamental thing we need to understand is all these books are sufficient to learn the concept and solve the basic level models and higher level models. But with regard to exam point of view, we should take care of the model based on the previous year question. That's all. Clear? Right. Any other things? Please ask your question if you have any other doubt. Yes, class notes is sufficient. That I am saying. Let me say one thing. If you have the previous year question bank with you, then you can check how many of the previous year questions are covered in the class itself. Right from 1992 onwards, as per the class topics going on. I have taken care of covering almost 90% of the problems based on the previous year question. 90% of the previous year questions are covered in the class sessions itself. Yes. Have you referred them? So for the upcoming sessions, while dealing with the silo theorems, finite fields, nothing but field extensions, the remaining part will be covered. So my intention is, if you know to solve a problem based on similar kind, you can solve any kind of problem. We cannot stick on ourselves that the same question will be repeated again, but it has very light chances to come again, as per the previous year papers observed. That's it. So there is no need to practice more number of problems here. The only thing we need to do is we should refer the logic frequently or occasionally, you can say, as per our needs concerned with regard to abstract algebra. So once the logic is there in your mind, problems will be solved automatically. But if the question is given, which is nothing but a result, then you need to learn the result. There is no other alternative, because for each result the approach is different. So for problems, you are good enough to solve based on previous year questions. That's it.